Nuclear Energy, Key to Tomorrow. Produced by WQED for the Educational Television and Radio Center, in cooperation with the Westinghouse Electric Corporation and the Atomic Energy Commission. The subject, reactor types. Your host, Dr. Warren Witzig, Manager of Reactor Physics, Bettis Atomic Power Division.
Welcome to another discussion on nuclear energy, the key to tomorrow. In this meeting, we're going to talk about reactor types. You will recall that a reactor is really a machine which uses the fission process. You remember from some of our past discussions that the fission process, as an example, is the splitting of uranium-235 by a neutron. That is, when a neutron impinges upon uranium-235, the uranium splits, goes into two fission fragments, and also gives out with some additional neutrons. Now, these additional neutrons, if they go on to produce fission in more uranium nuclei, and we sustain this, we call it a chain reaction. Now, the nuclear reactor is really a device to sustain this chain reaction. We can catalog reactor types in many ways. As an example, we know that there must be fuel in a reactor. And so obviously we can catalog it on the basis of fuel. That is, does it use uranium, thorium, or what have you? We can catalog it on the type of coolant that we put through these fuel channels, coolant channels rather, I should say, through the fuel. We can also catalog it on the basis of the kind of neutrons that we have in here. That is, are they fast as they're born in fission? Are they slow as they've been moderated? As they've been moderated. Then we can talk about moderation and use that as a typing mechanism. Now, we're especially fortunate to have with us for this discussion a man who has played a very prominent role in reactor design. This is Dr. Sidney Krasik, the manager of the Central Physics and Mathematics Department of the Bettis Atomic Power Division of Westinghouse. Let us go to Dr. Krasik's office. Sid, how do you propose to start the discussion on reactor types?
Warren, the basic physical process in the nuclear power reactor is the fission process. Why don't we discuss that for a few minutes?
Fine.
In the fission process, a heavy nucleus, such as U-235, splits into two fragments of nearly equal mass, and it is the kinetic energy of recoil of those two fragments moving apart that produces the energy which is the source of heat in a nuclear power reactor. The remarkable thing about the fission of U-235 is the emission of neutrons which takes place during the fission process. The fission process, let us say, starts by the introduction of a neutron into the U-235 nucleus. The U-236 nucleus then fragments into these two halves, giving up kinetic energy, and then we have the emission of neutrons from the two fragments. On the average, there is an emission of 2.5 neutrons per fission. What this means is that some of the fissions that take place release 2 neutrons, others produce 3, and there are about an equal number of each, so that on the average, about 2.5 neutrons are emitted per fission. It is this emission of neutrons which makes the chain reaction possible, because we can see that if we have other U-235 nuclei present, that it's possible that one of the neutrons produced in this fission may be captured in the other U-235 nucleus, causing fission there. That in turn will emit some neutrons, and those may be captured in other nuclei. So the chain reaction process can take place if we have an array of U-235 nuclei arranged say, such as this, and let us suppose that this particular nucleus has fissioned, and it is going to produce 3 neutrons in this fission. Now, this neutron is going to leak out. This one leaks out. This one, however, moves up here, and if we were a little luckier, we would have captured that neutron in this nucleus. It would have fissioned, and let us say it would produce 2 neutrons, which might have been emitted in those directions. This one would leak out. This neutron would come down here, be captured in this nucleus, which would fission. Let us say this time there were 3 neutrons produced, and one of these, say, didn't leak out but was captured in this, and so forth. So that the chain reacting process takes place by the successive fissioning of U-235 nuclei from neutrons produced in previous fissioning.
Sid, this is the very heart of these reactors. Supposing we talk a little more just how we make sure that this chain reaction is sustained in a reactor.
Well, you can see what the problem is. The problem is basically this, that we have to assure ourselves that for every fission that has taken place, that one neutron from that fission gets captured in another U-235 nucleus. And the problem really is, can we assure that to take place before the neutron leaks out of the arrangement of U-235 nuclei? And clearly, one of the ways that we can do this is to have more uranium around so that there is a better chance for a capture and fission to take place before the neutron leaks out of the arrangement. And so by adding fuel, we can make the assembly more likely to react. Now, there is another problem that is involved here, and that is the target size. That is, what is the chance that a neutron moving off in this way will be captured in one of these nuclei? And that depends on the target size of the nucleus. If we have an arrangement such as this with a target size shown in this way, and one of the neutrons moves through the arrangement of nuclei, then there is a pretty good chance that it will move through without being captured. On the other hand, it might be that the target size of the nucleus is larger than that. And if the target size is larger, there is a better chance of it getting through before it leaks out of the reactor. So in a situation like this one, where the target size is larger, there's a much better chance of the neutron causing a fission in the U-235 before it leaks out of the reactor. So it is the combination of these two things, Warren, the combination of the target size of the nucleus and the number of nuclei that are present, which are the ways that we can adjust and maintain the criticality of the arrangement. Now, let's talk a little bit about this question of target size, or in terms used in nuclear physics, the cross-section of the nucleus. That is, the target size of the nucleus to this event is called its cross-section. One of the interesting features of nuclear physics is the variation of this cross-section with the speed of the neutron. The neutrons which are emitted in this fission process are quite energetic. The nuclear physicist measures the energy of the neutron in electron volts, and the neutrons which are emitted in fission have an energy between 1 and 2 million electron volts on the average. Translated in other terms, this means that we can say that their speed is something like 10,000 miles per second, which is pretty fast. Now, if the neutron, instead of having an energy of 1 to 2 MeV and this kind of a speed, had an energy that was a millionth of this, say 1 electron volt instead of a million, and its speed would be correspondingly reduced, say to something like 10 miles per second, which is still pretty fast, but we will consider it to be relatively slow, then the target size of this nucleus to that neutron is about 50 times as large. So it is possible, by changing the energy or the velocity of the neutrons, the speed of the neutrons, to change the effective target size of the U-235 nuclei and thereby be able to maintain the chain reaction with fewer nuclei present.
So this is a very interesting concept, this neutron speed. Supposing we illustrate the speed effects.
Well, imagine that we have a pool table, and suppose that we have a billiard ball on this pool table and something lighter than the billiard ball, much lighter, like a ping pong ball. Then if the ping pong ball strikes the billiard ball, it will bounce off and it won't change its speed very much. The direction that it moves will be changed, but its speed will be relatively unaffected, and the billiard ball will stay put. This is like what happens when a neutron strikes a heavy nucleus. The neutron recoils from the heavy nucleus without changing its speed.
Such a heavy nucleus might be, in contrast to the fissionable material, the structural material in a reactor.
The structural material in the reactor, such as zirconium or iron, something like that. On the other hand, suppose that we have on our on this billiard table 2 billiard balls, which are about the same mass, so that one billiard ball moves up and strikes the other. Then, because they have about the same mass, if we have a head-on collision, one billiard ball will move ahead, taking up the speed of the first billiard ball. The other one will remain stationary. Suppose that they make a glancing collision. Then both of them will move off at angles to each other, and each of them will share in the energy. But the idea is this, that by having the neutron strike a nucleus which has about the same mass as the neutron, it is possible for the neutron to give some of its energy up to this other nucleus and to be slowed down. This other nucleus is the so-called moderator material. And you can see from this discussion that what we want in a moderator material is a light nucleus having a mass comparable to that of the neutron. Such a moderator material might be hydrogen. Hydrogen has a mass which is very close to the neutron, and therefore, from the point of view of slowing the neutron down, is very efficient. Another useful moderator material might be deuterium, the heavy hydrogen, which has about twice the mass of the neutron. Other useful moderator materials are carbon or beryllium. So that by the use of the moderator, we are able to slow down the neutron.
All right, Sid, let me summarize then the important features that we've covered with regards to what makes these reactors go. We've reviewed the fission process, and then we've gone on to say that this process must be a chain reacting one. That is, it must continue. And we've discovered that there are really two important things to see that it does continue. One of them is that we have enough uranium, and we illustrated that by packing more uranium in our reactor. And the other is that we can change the target size of that uranium, for neutrons at least, by changing the speed of the neutron. And here we introduced the idea of the moderator, which does change the speed of the neutron. Now this automatically gives us a sort of a reactor type, doesn't it, sir?
Yes, while we're on this particular subject of the speed of the neutrons, we might just point out, Warren, that a reactor can be classified according to the speed of the neutrons, which are the cause of the fission. For example, if we don't moderate the neutrons, that is, if their energy is essentially that of the neutrons emitted in fission, we have what is called a fast reactor. The neutrons which are causing the further fissions have their maximum energy that they originally had. On the other hand, suppose that we put a lot of moderator nuclei in the reactor so that the neutron is slowed down. If it is slowed down so that its energy is comparable to the thermal energy of the moderator in the reactor, that is the thermal energy of agitation, then we call this a thermal reactor, and the neutrons are about as slow as we can make them. And if the reactor has neutrons of energy which are intermediate between fast and thermal, that are the main cause of the fission, then we call it an intermediate reactor. So reactors can be classified as fast, intermediate, or thermal, depending on the energy of the neutrons, which are predominantly causing the fission process to take place.
Sid, to help us carry on this reactor type classification, supposing we take a look at the hardware end of it.
I think, Warren, that perhaps we ought to take a look now at this reactor plant and see what a nuclear power plant looks like. What we have been talking about so far is the fission process taking place in the reactor core. This is the place that the chain reaction is taking place. This is where the heat is generated in the reactor. Now, in order to use this heat, we have a system such as this. The heat is produced here. It is removed from the reactor by a coolant, which is circulated by the reactor. The coolant temperature is raised, and it circulates around here to a boiler. At the boiler, the coolant transfers its heat to water. It makes steam. The steam moves over here, drives the turbine drives the generator, and we have electrical power coming out of the generator. Now, from here over to the right of this diagram, this is exactly similar in principle to the conventional power plants which use coal or oil as the fuel. That is, they burn, they produce steam, the steam drives the turbine, and so forth. The main difference in a nuclear power plant is the way the heat is produced. The heat in this case is produced in a reactor core. It is removed by a coolant which pumps through the core, takes the heat over to the steam generator or boiler. Now,
so really all we're doing in this schematic is to replace our coal-fired boiler by a nuclear-fired one.
Correct. Now, getting back to this question of classification, we've classified the reactors according to the neutron spectrum as being fast, intermediate, or thermal. We could classify the reactor by the moderator which is used. For example, it could be moderated with light water, it could be moderated with deuterium, beryllium, or graphite. So reactors can be classified according to a moderator. They can also be classified according to the coolant that is used. We might use ordinary water as the coolant. We might use a liquid metal. We might use a gas, such as helium or carbon dioxide. So there are many different ways of classifying a reactor, and there are very many different combinations of moderator, coolant, neutron spectrum, which may be used to make a power reactor. Now, I suppose that the question that immediately arises is, why worry about all these various types? Why not just pick one out and work on it and make it work? Well, this is a very interesting point because there are advantages to certain of these reactor types, and there are good reasons for working on many different ones. We've mentioned the fast reactor. One of the big advantages of the fast reactor is that it is possible with such a reactor to make a breeding system. That is a system in which you create out of fertile nuclei more fissionable nuclei in greater quantity than those you destroy. We'll talk about that a little bit later. So the fast reactor has the advantage of breeding capabilities. The thermal reactor has the advantage, as we saw before, that because the target size of the nucleus is so much larger, it requires much less fissionable material. That is, it takes a lot less U-235 in a thermal energy reactor to make a chain reacting, perhaps 1/10 of that it would take in a fast reactor. So the big advantage of the thermal reactor is the reduced quantity of fissionable material. There is one other point that ought to be brought out. None of these reactors are easy to build in a technical or engineering sense. All of them have some very real problems. The problems are different for the different kinds of reactors, depending on whether it's cooled with water, liquid metal, whether it's graphite moderator, gas cooled. And in a sense, by working on one or the other, you can choose the particular technical problem that you are going to work on. You can name your headache if you like. So the reason is that there are advantages and disadvantages of different types. There are various problems that arise in one. Now, there is one other class of reactor that we haven't talked about yet, and something should be said about that. We have implied that all the fissionable material is located here in the reactor core. It is possible to have a reactor type that's called homogeneous, in which the fuel, the coolant, the moderator is all mixed up into one solution, and the entire batch of solution is circulated through through the reactor and steam generator. Over here, it reacts and it raises its temperature. It moves over here, gives up its heat to the boiler. Now,
Sid, I'm going to have to interrupt you because of our limited time. Supposing we leave the homogeneous now and go to the heterogeneous and take a look at how it is built.
well, since we have so little time, Warren, perhaps we ought to limit ourselves to taking a look at a specific type
All
of
right,
reactor,
fine.
say a thermal reactor.
Fine.
And we have some diagrams over here illustrating what a fuel element structure in the core of such a reactor might be. Here is a typical fuel element that might be used in a ordinary light water-cooled reactor. These rods are uranium fuel rods. They are clad with a cladding material which keeps the fission products from getting from the fuel element into the coolant water. The coolant water flows by these tubes. Now, these tubes can be something order quarter to a half inch in diameter, and in a light water reactor, they are spaced a half, three quarters, or about an inch apart. I have here a model of I have a small section, actually, of a fuel element which is used in the shipping port reactor, which was placed in operation in 1957. These are the tubes of zirconium which contain the uranium inside. These are the spaces here through which the coolant flows, taking the heat out of the reactor. Of course, the actual reactor has many more fuel elements than this. It might have 50,000 or 100,000 such tubes making up the complete reactor. And typically, a reactor of this size might be about 6 feet in diameter by about 6 feet high. I can have another type of light water moderated reactor with a plate type fuel element. In this reactor, the fuel is located in the plates here, shown by the heavy lines. The coolant passes up these spaces between the plates, taking the heat away from the plates. Typically, an element like this might be 2 or 3 or 4 inches square, and there might be 200 or 300 of them making up the entire reactor. Now, I have one other example here of a gas-cooled graphite moderated reactor, which is the type that was placed in operation in Britain in 1956. This is the Calder Hall type reactors. These are the fuel elements here. They are surrounded by channels through which the gas coolant flows, taking the heat away from the fuel element. This is the graphite moderator blocks between adjacent elements, and typically the space here might be 6, 8, or 10 inches, so that a reactor which is graphite moderated is typically very large compared to the light water reactors of the order of 20, 30, or 40 feet in diameter by 40 feet high.
Now, we've shown an example here, then, of different kinds of coolants, all in the slow kind of reactor, Sid. Could we take a look at our fast reactor?
Yes, I think it would be a good idea to go back to this point of breeding, which we mentioned in passing, just to get an idea of how it works. Now, U-238, which is the common isotope in natural uranium, is what is called a fertile material. If a neutron enters U-238 and is captured by it, it forms U-239. The U-239 is unstable and decays through the emission of a beta particle to Neptunium-239. This, in turn, decays to plutonium-239 by the emission of another beta particle. The remarkable thing is that plutonium-239 is a fissionable material, much like U-235, and can therefore be used in a reactor. So by using some of the neutrons which are formed in the chain reaction, we can convert U-238, the fertile material, into a fissionable material, plutonium-239. The same thing can be done with thorium. Thorium can be converted into an isotope of uranium, which is also fissionable. In the fast reactor, the core of the reactor contains U-235, let us say, so that the reactor is operating on U-235 as a fissionable material. It is a small compact reactor with no moderator. It has only the coolant in it, and it is of such size that it leaks neutrons out to what is called a breeding blanket, which is composed principally of U-238. So in the fast reactor with the breeding blanket system, the chain reaction is maintained by the fast reactor itself, fueled with U-235. The neutrons leaking out are captured into the U-238 breeding blanket, which eventually forms the plutonium-239. The remarkable feature of the fast reactor system is that it is possible with a system like this to make more plutonium-239 than you destroy uranium-235, so that we have a breeding gain possible greater than 1. We can make more fissionable material than we use up. In a thermal reactor, we can make some fissionable material, but we cannot make more than we use up. Warren, I think that we've probably covered some of the main features of power reactor systems in this brief description.
Yes, I think we have, Sid. On behalf of our viewer, I'd like very much to thank you for giving us your time.
Very well.
As you can see from our discussion with Dr. Krasik, there are many ways that we can catalog these reactors. Let's just review them. We've talked about cataloging them as fast and slow, depending upon the neutron energy. We've talked about cataloging them with respect to fuel. We've talked about cataloging them with respect to coolant. Is it gas? Is it water? Is it a liquid metal? We've talked about cataloging them on the basis of, are they heterogeneous or homogeneous? That is this reactor limited to having the fissionable material here, or is the fissionable material distributed throughout the system? These are the principal ways that we talk about reactor types. It's been a real pleasure to discuss these things with you on reactor types, and we want to make sure that you come back and are with us when we talk about some of the future aspects of nuclear energy, the key to tomorrow.
Nuclear Energy, Key to Tomorrow. Produced by WQED for the Educational Television and Radio Center, in cooperation with the Westinghouse Electric Corporation and the Atomic Energy Commission. The subject, reactor types. Your host, Dr. Warren Witzig, Manager, Reactor Physics. Special guest, Dr. Sidney Krasik, Manager of Central Physics and Mathematics Department. Technical advisor for the series, Mr. Edward Sanford. Engineering supervision by Frank Stuckman and Stephen Zorbas. Production and direction for the series by John W. Ziegler and Robert Potts. This is National Educational Television.